Alright guys, we're back with the full adder design. Now in the last video, we took a look at the half adder design, which actually just took two bits and added them together and then produced a sum and then also a carry. And that worked just fine for only adding two bits together. So the problem came when we tried to start adding strings of bits. So 2 bits, 3 bits, 4 bits. And each power of 2 after the very first position had to take into account one of the carry bits from the prior position of 2. So the issue with that was that it wouldn't take into account adding in the carry bit in addition to the 2 bits that we were actually adding in that position of the power of 2. So in this case, we need to go back to the drawing board, rewrite a new truth table that would actually take into account that carry bit up front and then produce a new output of sum and a new output of carry. So that's exactly what we did here. We basically, Nick Saban went back to the board because he didn't beat Auburn this past season. So he had to go through and design a new gameplay. That's what we had to do here, guys. Bam, here it is. So basically A, B, and the carry are now our inputs, and now we have a new sum and a new carry that we're actually utilizing for the outputs. So 0 plus 0 plus 0 gave us 0 with a carry of 0. 0 plus 0 and with a carry of 1 gave us 1 with a carry of 0. 0 plus 1 with a carry of 0 gave us 1 with a carry of 0. But if we had 0 plus 1 and then also a carry of 1 on top of that, that gave us an output of 0 with the carry. And actually, as we step down, the only difference that we'd actually see in basically the prior half adder and then the new half adder would basically be anytime we actually saw a carry bit of 1 that came into account. But down here, when we took A and B, if they were both high, add those together, we know that that equals 0 with a carry of 1. However, if the carry in bit was also 1, then that 1 falls through, and so we get a summation of 1 with a final carry of 1 itself. So the full adder's truth table takes into account everything that we're actually considering in terms of the possibilities for which we're adding 2 bits together, and also considering the carry from the prior position of a power 2. So all we had to do here is go right back to the K-map, but instead of a 2-input K-map, we have a 3-input K-map. Go through and add out this for the summation. The sum, oh yeah, we couldn't group any of those, so all these were just grouped by themselves. But down with the carry, we actually had four of these in which the output went high, and then we were able to basically do 3 groups of 2 each. So the implementation of this is actually quite a bit more complex than the half adder itself. So I didn't write out the actual Boolean expression for the summation of the full adder or the Boolean expression for the carry, but it's pretty easy to see that this would be A bar, B bar, C, A bar, B, C bar, A, B bar, C bar, and then A, B, C. And that's exactly what we did here. So this portion of the full adder represents the logic that we need in order to get that summation right there. And so basically we take bus bars, basically A, B, and C, or the carry, and then actually get an inverted bus as well. And then all we did was just tap off for each portion, each min-term of that Boolean expression that we would have gotten from optimizing the K-map. And then basically take those 4 terms, and then basically all we do is OR all of them together. Summation of min-terms, just like we've been doing. Down here for the carry, same thing, guys. Basically just optimize it. We were able to do a little bit of cancellation of a couple of literals, so we're able to basically just take 3 AND gates, take the appropriate inputs, OR them together. And that we actually have as basically being the full adder. And with the full adder, we get a little bit different of a block diagram. And so the block diagram is just a little bit simple, because if we had 64 bits, I don't think you guys actually want to draw that 64 times. No, 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 no. So the block diagram that we utilize would be this. So basically just a block that we would actually tack on and say full adder, in which we get the sum and then also the carry. But the inputs would actually be A, B, and then carry, in which I'm going to put prior next to it. So the full adder has 3 inputs and then just 2 outputs. So what we're going to be doing in the homework for this one is I'm going to have you guys basically design me a full diagram that actually shows the appropriate combination of the half adder and full adders in order to actually add 4 bits together. So I'll take a look once you guys send those in to me. Alright, see you next time.